नमस्कार, मैं आनंद कुमार खत्री, एसोसिएट प्रोफेसर ऑफ जूलॉजी, गवर्नमेंट डूंगर कॉलेज बीकानेर। आज के हमारे लेक्चर का विषय है हाइड्रोस्फीयर, पार्ट 5। जैसा कि हमने हाइड्रोस्फीयर के 4 पार्ट ऑलरेडी पढ़ लिए हैं, उसी के कंटिन्यूशन में ऑरिजिन एंड इवोल्यूशन ऑफ द हाइड्रोस्फीयर। इट इज़ नॉट very likely that the total amount of water at Earth's surface has changed significantly over geologic time. Based on ages of meteorites, Earth is thought to be 4.6 million years old. The oldest rock known are 3.9 million to 4.0 billion years old. And these rocks, though altered by post depositional processes, shows sign of having been deposited in an environment containing water. There is no direct evidence for water for the period between 4.6 billion and 3.9 to 4 billion years ago. Thus, ideas concerning the early history of the hydrosphere are closely linked to theories about the origin of Earth. Earth is thought to have accreted from a cloud of particles around the Sun. These gaseous matter condensed into small particles that coalesced to form a protoplanet, which in turn grew up by the gravitational attraction of more particulates. Some of these particles had composition similar to that of carbonaceous chondrite meteorites, which may contain up to 20% water. Heating of this initially cool, unsorted conglomerate by the decay of radioactive elements and the conversion of kinetic and potential energy to heat resulted in the development of Earth, liquid iron core, and the gross internal zonation of the planet. That is the differentiation into core, mantle, and crust. It has been concluded that Earth's core formed over a period of about 500 million ago. It is likely that core formation resulted in the escape of an original primitive atmosphere and its replacement by an one derived from the loss of volatile substances from the planetary interior. At an early stage, Earth thus did not have water vapor at its surface, and the topic of how water arrived on Earth's surface is a matter of substantial debate. Some scientists argue that much of the water on the planet was delivered by comet and meteorite impact. Both of these celestial objects have been shown to contain ice. Other scientists claim that most of Earth's water comes from chemical reaction within the planet's interior. Once the planet's surface had cooled sufficiently, water contained in the minerals of the accelerated material and released at depth could escape to the surface, and instead of being lost to space, cooled and condensed to form the initial hydrosphere. A large cool Earth most certainly served as a better trap for several than a small hot body, because the lower the temperature, the less likelihood of water vapor to escape, and the larger the planetary mass. The stronger its gravitational attraction for water vapor, whether most of the degassing took place during core formation or shortly thereafter, or whether there has been significant degassing of Earth's interior throughout the geological time, remains uncertain. It is likely that the hydrosphere attains its present volume Earth's history, and since that time there have been only small losses and gains. This is a diagram of the इंटीरियर स्ट्रक्चर ऑफ द अर्थ, जिसमें आपको क्रस्ट दिखाई दे रहा है माइल्स में कितने ही 3 to 19 miles एवरेज. Earth's major structural layer displayed in cross sections near surface and surface features such as an ocean basin and continents also shown in this cross section. Gains would be from continuous degassing of Earth. The present degassing rate of juvenile water has been determined as being only 0.3 cubic kilometer per year. Water loss in the upper atmosphere is by photodissociation, the breakup of water vapor molecules into hydrogen and oxygen due to the energy of ultraviolet light. The hydrogen is lost of space and the oxygen remains behind. Only about 4.8 into 10 to the power minus 4 cubic kilometer of water vapor is presently destroyed each year by photodissociation, and the low rate can be readily explained. The very cold temperature of the upper atmosphere result in a cold trap at an altitude of about 15 km, where most of the water vapor condenses and returns to lower altitude, thereby escaping photodissociation. Since the early formation of the hydrosphere, the amount of water vapor in the atmosphere has been regulated by the temperature of Earth's surface, hence its radiation balance. Higher temperatures imply higher concentrations of atmospheric water vapor, while lower temperatures suggest a lower atmospheric level. The early hydrosphere, the gases released from Earth during its early history, including water vapor, have been called excess volatiles because their masses cannot be accounted for simply by rock weathering. These volatiles are thought to have formed the early atmosphere of Earth at an initial crucial temperature of about 600 degrees centigrade. Almost all of these compounds, including water, would have been in the atmosphere. The sequence of events that occurred as the crust cooled is difficult to reconstruct. Below 100 degrees centigrade, of all of the water would have condensed, and the acid gases would have reacts with the original igneous crustal minerals to form sediment and an initial hydrosphere that was dominated by a salty ocean. If the chemical reaction rates are assumed to have been slow relative to cooling, an atmosphere of 600 degrees centigrade would have contained, together with other compounds, water vapor, carbon dioxide and chloride, in a ratio of 20⁻³ and cooled to a critical temperature of water, that is, the temperature above which a compound cannot remain as a liquid, that is 374 degrees centigrade. The water therefore would have condensed into an early hot ocean. At this stage, the hydrogen chloride would have dissolved in the ocean about 1 mole per liter, but most of the carbon dioxide would have remained in the atmosphere with only about 0.5 mole per liter in the ocean water. This early acid ocean would have reacted vigorously with crustal minerals, dissolving out silica and cations and creating a residue composed principally of aluminous clay minerals that would form the sediments of the early ocean basins. This is the comparison of Earth's periodic and modern atmosphere. This is one of the several possible pathways for the early surface of Earth. Whatever the actual case, after Earth's surface had cooled to 100 degrees centigrade, it would have taken only a short time of the remaining acid gases to be consumed in reaction involving igneous rocks, minerals. The presence of cyanobacteria, blue-green algae, in the fossil record of rocks older than 3 billion years attests to the fact that Earth's surface had cooled to temperature lower than 100 degrees centigrade by this time, and neutralization of the original acid volatiles had taken place. It is possible, however, that because of increased greenhouse gases concentration early in the Archean eon, 4.0 billion to 2.5 billion years ago, Earth's surface could still have been warmer than today. If most of the degassing of primary volatile substance from Earth's interior occurred early, the chloride released by the reaction of hydrochloric acid and with rock minerals would be found in the ocean or in evaporite deposits, and the ocean would have a salinity and volume comparable to that of today. This conclusion is based on the assumption that there had been no drastic changes in the ratio of volatiles released through geologic time. The overall generalized reaction indicative of the chemistry leading to the formation of the early ocean can be written in the form: primary igneous rock minerals plus acid volatiles plus H2O equals to sedimentary rocks plus ocean plus atmosphere. It should be noted that from this equation that if all the acid volatiles and H2O were released early in the history of Earth and in proportion found today, then the total original sedimentary rock mass produced would be equal to that of the present, and ocean salinity and volume would be close to that of today as well. If one of the other hand degassing were linear with time, then the sedimentary rock mass would have accumulated at a linear rate as would have oceanic volume. The salinity of the ocean, however, would remain nearly the same if the ratio of volatiles degassed did not change with time. The most likely situation is the one presented here, namely that major degassing occurred early in Earth's history, after which minor amount of volatiles were released especially or continuously for the remainder of geologic time. The salt content of the ocean based on the constant proportion of volatiles released would depend primarily on the ratio of sodium chloride locked up in evaporite to that dissolved in the ocean. If all the sodium chloride in evaporite were added to the ocean today, the salinity would be approximately doubled. This value gives a sense of the maximum salinity that the ocean could have attained throughout geologic time. One component absent from the early Earth's surface was free oxygen. It would not have been a constituent released from the cooling crust. Early production of oxygen was by the photodissociation of water in Earth's atmosphere, a process that was triggered by the absorption of the sun's ultraviolet radiation. The reaction is H2O plus ultraviolet radiation H plus O, in which UV represents the photons of ultraviolet light. The hydrogen produced would escape into space while the oxygen would react with the early reduced gases by the reactions such as 2H2S plus 3O2 equal to 2SO2 plus 2H2O. Oxygen production by photodissociation gave the early reduced atmosphere a start toward present day condition. But it was not until the appearance of photosynthesis organism approximately 3 billion years ago that oxygen could accumulate in Earth's atmosphere at a rate sufficient to give rise to today's oxygenated environment. The photosynthetic reaction leading to oxygen production is given in equation 6. The transitional hydrosphere. The nature of the rock record from the time of the first sedimentary rock, approximately 3.8 billion years ago to about 1 to 2 billion years ago, suggests that the amount of oxygen is in Earth's atmosphere was significantly lower than it's today, and that there were continuous chemical trends in the sedimentary rock form and more subtly in the composition of the hydrosphere. The chemistry of rocks shifted dramatically during this transitional period. The source rocks of sediments during this time may have been more basaltic than subsequent one. Sedimentary debris was formed by the alternation of such source rocks in an oxygen deficient atmosphere and accumulated primarily under anaerobic oxygen free marine condition. The chief difference between reaction involving mineral ocean equilibria at this time and the present day was the role played by ferrous iron, that is, reduced state of the iron. The concentration of dissolved iron in modern ocean is low because of the insolubility of oxidized iron oxides. During the transitional stage and earlier, oxygen deficient environments were prevalent, and these favored the formation of minerals containing ferrous iron from the alternation of rocks slightly more rich in the salt than those of today. Indeed, iron carbonate siderite and iron silicate granulite in close association with chert and iron sulfide pyrite are characteristic mineral that occur in the iron formation of the middle Precambrian. The chert originally was deposited as amorphous silica equilibrium with between amorphous silica saturite and granulite at 25 degrees centigrade, and a total pressure of 1 atmosphere requires a carbon dioxide pressure of about 10 raised to minus 2.5 atmosphere, or 10 times at the present day value. The ocean of the transitional period can be thought of as a solution that result from an acid leach of basaltic rocks, and because of the neutralization of the volatile and acid gases was not restricted primarily to land areas as it is today. Much of this alteration may have occurred by submarine processes, anaerobic deposition environments with internal carbon dioxide pressures of about 10 raised to minus 5 atmosphere prevailed, and the oxygen deficient atmosphere itself may have had a carbon dioxide pressure close to 10 raised to minus atmosphere. If so, the pH of early ocean water was lower than that of modern seawater, and the calcium concentration was higher. Moreover, the early ocean water was probably saturated with respect to amorphous silica, roughly 120 parts per million. To simulate what might have occurred, it is helpful to imagine empty the Pacific basin, throwing in great masses of broken basaltic material, filling it with hydrogen chloride dissolved in water so that the acid becomes neutralized, and then carbonating the solution by bubbling carbon dioxide through it. Oxygen would not be permitted into the system. The hydrochloric acid would leach the rocks, resulting in the release and precipitation of silica and the production of a chloride ocean containing sodium, potassium, calcium, magnesium, aluminum, iron, and reduced sulfur species in the proportion present in the rocks. As complete neutralization was approached, the aluminum could begin to precipitate as hydroxides and then combine with precipitated silica to form cation deficient aluminosilicate. As the neutralization process reached its end, the aluminosilicates would combine with more silica and with cation to form such mineral as chlorite, and ferrous iron would combine with the silica and sulfur to produce granulite and pyrite. In the final solution, chlorine would be balanced by sodium and calcium in roughly equal proportion, with subordinate amounts of potassium and magnesium. Aluminum would be quantitatively removed, and silica would be at saturation with amorphous silica. If this solution were then carbonated, calcium would be removed as calcium carbonate, and the chlorine balance would be maintained by abstraction of more sodium from the primary rock. The sediment formed in this system would contain chiefly silica, ferrous, iron, silicates, chloritic minerals, calcium carbonate, calcium magnesium carbonate, and a small amount of pyrite. If the hydrogen chloride added were in excess of the carbon dioxide, the resultant ocean would have a high content of calcium chloride CaCl2 but with a pH still near neutrality. If the carbon dioxide added were in excess of the chlorine, calcium would be precipitated as carbonate until it reached a level roughly that of present day ocean water, namely a few hundred parts per million. If this newly created ocean were left undisturbed for several hundred million years, its water would evaporate and the transported in the continents. Streams would transport their loads into it. The sediment produced in this ocean would be uplifted and incorporated into the continents. The influence of the continental debris would gradually be felt, and the pH might change somewhat. Iron would be oxidized out of the ferrous silicate to yield iron oxides, but the composition of the water would not vary substantially. The primary minerals of igneous rocks are all mildly basic compounds. When these minerals react in excess with acids such as hydrogen chloride and carbon dioxide, they produce neutral or mildly alkaline solution as well as a set of altered aluminosilicates and carbonates reaction products. It is improbable that seawater has changed through time from a solution approximately in equilibrium with these reaction products, that is with clay minerals and carbonates. Thanks.